Hi, today we are going to learn about hybridization. Hi, today we are going to learn about hybridization. Hybridization is a very important concept in chemistry which actually helps us predict the molecular geometry of different compounds. By molecular geometry, what I mean is how does those compounds look like in 3D space. So to learn about hybridization, let's take an example of CH4, which is generally known as methane. So at the end of this video, we'll be able to predict the molecular geometry or how does a molecule of CH4 looks like in 3D space. Now for that, let's write the electronic configuration of carbon. We have already seen how to write electronic configurations in atomic structure videos. So for that, we need to know the atomic number of carbon, which is 6. Now, first will be my 1s orbital. First will be my 1s orbital. So here, let me draw the orbital box diagram also. So this is my 1s orbital. How many electrons can go into the 1s orbital? So if we recall, there are maximum 2 electrons which can go into one orbital. So it will be 1s2. And here I will draw the electrons which will be of opposite spin. My next orbital will be 2s. Here I will draw the box diagram also. So this is my 2s. So here also there will be 2 electrons and I will draw these 2 electrons here with the opposite spin. Now we have come up to 2p orbital. So my 2p subshell can have 3 orbitals. My 2p subshell can have 3 orbitals, which is 2px, 2py and 2pz. Each of these orbitals can have maximum 2 electrons, but how many electrons we are left with? So we have already consumed 2 plus 2, 4 electrons. We are only left with 2 electrons. So it will be 2p2 and there will be 1 electron here and 1 electron here. So these two are my unpaired electrons. Now let's just visualize how the atom of carbon looks like here. So I have the nucleus at the center. Then I have this 1s orbital, and there are 2 electrons in this 1s orbital. Then I have my 2s orbital, let's say. This is my 2s orbital and there are 2 electrons in this 2s orbital also. Now to talk about p orbital, let me draw the axis first. So this is my y-axis, this is my x-axis and this is my z-axis. It's not going from the middle of it, but let's assume it is going from the middle of the nucleus. So how does my p electrons will look like? This will be my, let me take some other color. So this will be my px orbital. This will be my px orbital. This will be my pz orbital. And the last one, this will be my px orbital. Px orbital. We know that there are 2 electrons in 1s orbital, there are 2 electrons in 2s orbital and there are 2 electrons in p orbitals. And let's assume that one of the electron is there in px. Let me draw the electron like this. One of the electron is there in px and the other one is there in py. So there are total 6 electrons. So this is how a single carbon atom in this case looks like in the 3D space, if we have to imagine it like this. Now here in the case of CH4, 4 hydrogen atoms has to bond with 1 carbon atom. For that, let me write the electronic configuration of hydrogen, which is 1s1. The electronic configuration of carbon is 1s1. And if I draw the box diagram, this is my 1s orbital and there will be only 1 electron, which is an unpaired electron. and I want these four hydrogens to combine with a carbon to form a molecule of methane. Basically, it has to bond with carbon. So here comes the fun part. Whenever carbon try to combine with hydrogens, or whenever carbon tries to bond with these hydrogens, what happens here is this particular electron. So this is my electron. This particular electron gets excited and it goes into the 2p orbital. This was my ground state of carbon. So this is called my ground state of carbon. And if I have to write this excited state where this electron is going in, it's exciting and going into a 2p orbital, then I'll write it as C star. So this is my excited state of carbon. We write it down, excited state. It will look something like this. This is my 1s orbital. 1s orbital will be same. There are two electrons with opposite spin. This is my 2s orbital. Now only one electron is remaining because the other electron has shifted to 2p orbital. So 2p orbital looks something like this. Now there will be one electron in 2px, 2py and 2pz. Now here comes the interesting part. So in the previous videos we learned about VBT, valency bond theory. In that we learned that any atom, if he has to make a bond, a covalent bond with any other atom, there is orbital overlap happens. So actually this 2s orbital can overlap with 1s orbital of hydrogen, and these 2p orbitals can also overlap with 1s orbital of hydrogen, and they can make bonds. But whenever but in that case there will be one bond of 2s and 1s, and there will be 3. So there will be total one bond of 2s and 1s overlap, and three bonds of 2p and 1s overlap. So if we have to actually look at the bond lengths and bond angles of CH4, my one bond length, so this is my one bond length which is of 2s and 1s, should be different from the other three bond lengths which is of 2p and 1s, So this is my 2s and 1s. But experimentally we found out that in CH4 all the four bond lengths are equivalent or equal, Now that's why we are actually learning the concept of hybridization. So in hybridization, what do we say? In hybridization we say that this was my 1s orbital of carbon. Again quickly let me write it. So this was my 2s and this was my 2p, where one electron each. So in hybridization we say that these all four orbitals, they combine together and make four hybrid orbitals. And they are of equal energy. They are of equivalent energy, which looks something like this. So here I have four hybrid orbitals and I'll call them sp3. Why sp3? Because there is one s orbital and 3p orbitals. That's why I'll call it as sp3 orbital. So I have got four sp3 hybrid orbitals here, and one electron each. These are unpaired electrons, each in all the hybrid orbitals. Okay, let me explain this with a diagram here. So this was my s orbital, this was my p orbital, this was my px, let's say, this was my pz. S, P, Px, Py and Pz. They all intermix together. They all all the four orbitals, they mix together and give me four hybrid orbitals. Now how does those four hybrid orbitals look like? They look they look something like this. So there is a bigger lobe. This lobe will be a little bit bigger, but let's assume this is a bigger lobe and this is a smaller lobe. So smaller lobe. And we'll get four hybrid orbitals like this. Sorry, four hybrid orbitals like this. They'll be of same shape and equal energy. Now, if I have to arrange these four hybrid orbitals in 3D, they look something like this. So, this is my one hybrid orbital. Let me take some other color. This is my other hybrid orbital. Then third one. This is my third hybrid orbital. And last is my fourth hybrid orbital. So to keep the repulsions minimum, now because each and every orbital has one electron and they'll repel each other, these electrons will repel each other. Now to keep those repulsions minimum, these hybrid orbitals arrange themselves in a tetrahedral geometry. Now what does a tetrahedral geometry look like? So it is like there is a center, there is something above, and there is something in the same plane, and there is something coming out here and something going in. Okay, and all the angles in case of tetrahedral is 109.5 degrees, approximately this much. So all the angles here are same, and the repulsions will be least here. So if we have to imagine that how does these four hybrid orbitals look like, how they will arrange themselves in a 3D space, they'll arrange themselves like a tetrahedron. Okay, now I have four hydrogens also. I have four hydrogens. So this was my carbons, four hybrid orbitals. So my carbons, four hybrid orbitals. I have four hydrogens which has one electron each in 1s orbital. So 1 electron each. Now these four hydrogens will overlap with these four hybrid orbitals. This is my hydrogen. Let me take some other color here. Let me take this color. This is my hydrogen. This is my hydrogen. The third one and the fourth one. And one electron each. One electron each. So it has overlapped with the hybrid orbitals, and when it will overlap with the hybrid orbitals, it will make bonds of the same length, and the angles between all the angles here, the angles will be 109.5 degrees. So this is how a CH4 molecule will look like in 3D space. It will basically form a tetrahedron. So let me summarize this. CH4, it will form a tetrahedral with a carbon here, a hydrogen on top, a hydrogen here, a hydrogen like going inside, and one hydrogen coming out. It is like coming out of the plane. So, and this carbon we'll say is sp3 hybridized, because to bond with these hydrogens, one s orbital and three p orbitals, they intermixed together and formed four hybrid orbitals, four sp3 hybrid orbitals. Now some of the points to take down from this video is, whenever hybridization is happening, the number of hybrid orbitals formed, so here we got four hybrid orbitals, is equal to the number of hybridizing orbitals. Here the hybridizing orbitals are one s orbital and three p orbitals. Therefore the number of hybrid orbitals will be equal to 4. because here I have 4 hybridizing orbitals. This is 1, 2, 3 and 4. 4 hybridizing orbitals equals to number of hybrid orbitals equals to 4. These hybrid orbitals will be of equivalent energy and they'll make, we say that they'll make stronger and stabler bond than the normal orbitals. If I have to make a bond, let's say, with a hybrid orbital, or if I have to make a bond with all these 4 orbitals, my hybrid orbitals will make stabler and stronger bond. Stabler and stronger bond. And stronger bond. So, from this video, we actually learned how does a molecule of CH4 looks like in a 3D space. By that, we learned about the sp3 hybridization. Now, there are different types of hybridization as sp and sp2, and in the next video, we'll also talk about the pi bonds.